Optimizing cycle time of CFT Outer in injection molding process. Abstract optimization of cycle time in injection molding process plays a critical role in plastic part production to increase process efficiency. At the same time, the price and quality of the finished part will not be affected. This paper explains the cycle time optimization of CFT Outer. The process parameters such as cooling time, cavity balancing, gate area improvement, and injection time are optimized, in which it contributes more in the cycle time. Experimental verification has been done with scientific injection molding process 6-step study in injection molding machine. The experiment results showed a way to achieve the goal of cost-effective way of optimizing the process. Keyword: CFT Outer, scientific injection molding, 6-step study, cooling time, cavity balancing, gate improvement. Introduction. Injection molding is one of the most widely used and important processes for the manufacturing of plastic part. The principal advantage of this process is to produce large volume of components in a short time. The injection molding process consists of melting of polymer and then injecting the melt into the cavity in the molds. After reaching the cooling temperature, the part is ejected from the mold. The injection, packing, cooling and component ejection are the main phases of the injection molding cycle. The main objective of this paper is to reduce the cycle time and increase the productivity. By varying parameters like injection time, speed, holding time, pressure, cooling. 2. Methodology. The scientific injection molding technique, which includes 6-step study, is used to optimize the process. The scientific injection molding is used in the production where small variations in molding variables can severely impact the process or finished product, which leads to increase in the productivity. The 6-step study refers to the viscosity curve, cavity balance, gate seal, process window, pressure drop, cooling time. The 6-step study, the viscosity, rheology, curve, gate freeze study and pressure drop analysis were the 3 experiments conducted as part of scientific molding studies. The molding area diagram, MAD, has reference in some early texts, including in Rosato's Handbook of Injection Molding, which was not always considered one. Suhas Kulkarni identified the MAD as the most effective and crucial step for deciding the robustness of the molding process. Cavity balancing is also important step 2. Fig 1. CFT Outer. Viscosity curve. To check the injection speed setting in the Newtonian range. Set the holding pressure to 0, make a short shot that fill 95% and note the fill time and peak injection pressure. Now lower the injection speed to 90%, 80% so on and note the fill time and peak injection pressure. Obtain the intensification ratio of the screw from the machine manufacturer. The value is 10. Observations. The injection speed to be set above 45 mm/sec, which is in the Newtonian region, since at this point the rate of change of viscosity is minimum. When the value is set and production is started, the voids were found in the parts and hence the injection speed is reduced to 35 mm/sec where the parts were with no voids. From the viscosity curve, the optimized injection pressure is determined. Cavity balancing. To understand the rate of melt injection, the cavity balancing study is done. The weight graph of the short shots from all cavities offers details on the filling balance between the cavities. A balanced filling of cavities guarantees an equal amount of material that is packed into the cavities, resulting the consistency of cavity to cavity. Set the speed of injection and time of holding that is obtained from the viscosity curve. Next, generate a short shot sequence, and record the weights of the cavity for each shot as in the above step. Depending on the size of the component, it is important to record at least 3 to 4 progressing shots, starting with the smallest short shot parts that can be make. Observations. During the conduction of experiment, it is seen that the left-hand cavity fills faster than that of the right-hand cavity. The mold has to be inspected for the change in dimensions between the right-hand cavity and left-hand cavity. For left-hand side gate, volume flow rate, Q, equals 306.1/3.77*1, equals 81.2 cc/sec. Shear rate rectangular gate equals 681.21,000, / 15.55 * 2.032, equals 7525 / SEC. For right-hand side gate. Volume flow rate, Q, equals 303 / 3.77 * 1, equals 80.3 cc / SEC. Shear rate rectangular gate equals 680.31,000, / 10.42 * 2.032, equals 11345 / SEC. The shear rate of RH is more when compared to LH. Pressure drop study to find where max pressure drop occurs. Set the injection speed and holding pressure as obtained from viscosity curve. Next, set the transfer position to push the flow through the stages, nozzle, sprue, runner, 1/3 RD 2/3 RD, and complete fill of part and record the peak pressure in each stages. Plot a graph of the peak pressure versus the flow section to generate the pressure drop graph. Observations. The experiment is conducted and graph is plotted. It is found that the pressure drop is high across the gate, about 4-5 MPa. This gives us the justification that the area of the gate is small and has to be improved. Process window is used to determine the holding pressure and the temperature of melt. The analysis of process window is carried out to find the limits within which aesthetically acceptable parts can be molded. Melt temperature, OC. Pressure, flash. Pressure, sink. Observations. The experiment is conducted and pressure and temperature are noted and connected to get the process window. It is seen that the process window is narrow and the possibilities of the part getting defects is more. The parts and mold has to be analyzed in IR image for better understanding of the process window. Gate seal study to determine the holding pressure at which the gate gets seal. Set the injection speed as viscosity curve. Set the process to center of the process window. Take at least 10 shots by increasing the holding time. Then take the shots and record the weight of parts. The gate seal time is the time at which the part weight stays constant. Observation. The graph gives the details of the part weight and the holding time. For different holding time, the weight of the part changes and the sink is formed until the holding time of 7 SEC. Hence the holding time is set at 8 SEC after injection. Cooling time study. This gives the efficiency of cooling. Calculate the discharge of the coolant flow at the inlet and outlet of the mold along the individual cooling lines using flow meter device. Calculate the surface area of the cooling channel using flow diameter, from the design. Find out the velocity of the flow using continuity equation. Action plan to improve the cooling line efficiency. The descalling of the cooling line is done. Air vents are improved in both the cavities. To improve the cavity balancing and to reduce the shear rate of RH, the gate area of RH is increased. For result, cooling time is reduced for about 16%. Overall viscosity dropped by 8.76%. Fill variation between the cavities dropped from 8.2% to 4.4%. Pressure drop across the runner area is reduced by 7.7%. Process window become larger by 60%. Gate seals at 10 SEC after injection time due to increase in the gate area and the reduction in injection time. Conclusion. In this study, optimization of process parameters and cycle time reduction in the injection molding process using scientific injection molding technique 6-step study, which has given many positive outcomes during the process that includes reduction in the part weight, which has been specified by the mold designer, reducing the energy consumption of the machine, reduction in overall cost per part has been achieved.